Good afternoon, 7th hour. I do apologize that I'm not there to be able to greet you and welcome you into the new year in person, and I thank you in advance for your flexibility as we begin our new year. Unfortunately, I had a meeting today, 7th hour, which means I was not able to be with you, but I promise I'll be back first thing tomorrow. As we continue to look ahead, semester 1 was a rousing success. I was incredibly pleased with our final exam results and with the grades for first semester. You should be very, very proud of yourselves for the learning and all of the chemistry you have acquired over the course of our first semester. Second semester, we take those pieces, those tools, sig figs, dimensional analysis, calculations, electron configurations, bonding, nomenclature. We take all these tools that you now have in your tool bag and we start to apply it forward. We really start to get into the meat and potatoes of chemistry. We get to look at chemical reactions. We get to see if we take two substances and we put them together, what will they make? What will it create? And we're actually going to get to the point where we can predict the future. Okay, if we have these two substances, what would we get? How would they react to make something new? So today we're starting our new unit. Unit 6 is chemical reactions. Now you may want a couple pieces from this video today. In the event that I'm moving a little too quick today, that's okay. You can yell at me when I get back. You can find this video online, posted on Blackboard under Unit 6. You can also pause at any point, ask our sub today to pause it for you, and then we will continue forward. All right? Here we go. Unit 6, chemical reactions. Now, what is going on here? Hey, now, some of you have seen this before. We've seen this on some of our other slides, but we haven't really stopped to digest or dissect what we see on the screen. On the screen before us, we've got a couple of things going on. We look and we see that we're actually starting with some substance, and then it becomes two smaller pieces. Now, wait a minute. There's a problem. It must be magic or something, because if you look at the beginning, we're starting with 3 oxygen, but we're ending with 2 oxygen. Aha! Must mean we are magicians, and we made oxygen disappear from existence. We cannot have that. And there's a reason we can't have that. And we've talked about it actually way back, I know it's been a while, way back in Unit 2 with the discussion of the law of conservation of mass. Law of conservation of mass says that matter, I really hope you all said, cannot be created nor destroyed during a chemical reaction. So as we start to look, we need to take care of some pieces. Now, chemical reactions, we had some signs. What were those 5 signs, those 5 indicators that a chemical reaction has taken place? Well, take a minute. If you'd be so kind, please pause the video. When you're ready, come on back and we'll see if we got the 5 indicators of chemical change. Welcome back. Those 5 indicators of chemical change are color change, energy change, either through heat or light, a smell or being produced, gas, bubbles evolving, or a precipitate forming. Now, if you remember, precipitate is a formation of a solid. You had 2 liquids, you didn't change the temperature, 2 liquids, you put them together, and a solid particle came out. If you see one of these 5 signs, that means a chemical change has occurred. You started with the substance and it has created something new. And we can actually show that using what we call a chemical equation. In a chemical reaction, this is the textbook definition, by definition, chemical reaction is the process by which one or more substances are changed into one or more different substances. Okay, chemical reaction, you start with some stuff, you make some new stuff. There's your scientific word of the day, stuff. Right? But there are some special stuffs we need to talk about. The starting substances in your chemical reaction are what we call reactants. They're the items, the chemicals that you began the reaction with. And those then reform, they recombine in such a way to create some products. Oh, cool. So reactants react to form products. Awesome. When you look at a balanced equation, you'll see a couple different parts. Okay? Here we see we've got our reactants. It's just like reading a sentence. We've got our reactants on the left-hand side. We've got our arrow, which indicates to us chemical reaction has occurred. And then we have our products to the right side of the arrow. However, we're ignoring the law of conservation of mass. If you go back to that reaction, that equation, you'll notice we started with 2 carbon on the reactant side, and we only ended with 1 carbon on the product side. You can't have that. You can't have particles or atoms just disappear. They have to go somewhere. You have to have the same substances you started with at the end of the reaction. So we need to pay attention and give some credence to the law of conservation of mass. Law of conservation of mass says that the mass of the reactants must equal the mass of the products. We saw this in Unit 2. We could add up the mass of all the reactants, find the mass of all the products, and those two have to be the same. This means mass is neither created nor lost during chemical reaction, our definition of the conservation of mass law. To do this in a chemical reaction, we're going to use a tool called coefficients. Coefficients, for all of you math savvy folk out there, coefficients are the numbers that you find in front of variables. In chemistry, we find the coefficients in front of our compounds. So we're going to use some numbers to get the reactant side of our equation, chemical equation, to be the same as the product side of our chemical equation. So C2H2 plus O2 turning into carbon dioxide and water actually becomes 2C2H2 plus 5 O2s to give us 4 CO2s and 2 H2Os. We call these large whole numbers coefficients. Now notice we didn't change the subscripts. We don't want to change the molecules. We know that we have to have viable compounds. They have to be balanced in terms of their charges. We therefore can only change, when balancing our equations, we can only change the coefficients. Now just like in math, your coefficient multiplies to all of the variables in our given substance. Here, our coefficients will be multiplied to all of the elements in our compound. So what this 2 actually tells us is that there's 4 carbon on the reactant side now. If we go over to the product side, we have 4 times our 1 carbon, we have 4 carbon on the product side. We have now 4 hydrogen, and 2 times 2 gives us 4 hydrogen. And we have 10 oxygen on the reactant side. Well, if we go over to our product side, we see we have 4 times 2 in the carbon dioxide. There's 8 oxygen. We're still missing 2. If we look, we have 2 oxygen provided from the water. So it's kind of like a seesaw, a teeter-totter. The reactant side of your seesaw has to be the same as the product side of your seesaw. Cool. So let's go back and revisit that starting substance, that starting equation. So we've got Na, Na. Oh, well, that's cool. If this is our seesaw, here's our pivot points right at that arrow. The reactant side of the seesaw must be the same as the product side of the seesaw. Well, we got 1 sodium here, 1 sodium here. They're good. Don't have to do anything. We have 1 chlorine on the reactant side. We have 1 chlorine on the product side. Also good. We have 3 oxygen on the reactant side and only 2 oxygen on the product side. Oh, well, we need to make it so that both sides are the same. Well, what's the smallest number that both 3 and 2 go into? That would be 6. So how are you going to make this side, this reactant side, have 6 oxygen? We would use our coefficient. We would need a coefficient of 2 to make 6 oxygen. Well, now if we have 6 oxygen on the reactant side, we better have 6 oxygen on the product side. What times O2 gets you to 6? We would multiply by 3. Now here's the catch. Because we changed the coefficient on this starting reactant, we now have to look at how that affects the other elements. Well, this now says we have 2 sodiums. That coefficient multiplies everything in our compound. Now we have 2 sodiums. Well, okay, if we got 2 sodiums here, we better have 2 sodiums on the product side. We're then going to go ahead and put a 2 for the coefficient in front of our sodium chloride. This then creates a viable chemical reaction. Notice we didn't change any subscripts. You can't just change the subscripts. That changes the compound. Can't do that. We're only going to change the coefficients. Okay? If you're feeling comfortable, let's go ahead and take a look at our homework. Let's go ahead and look at the first item on your homework sheet. Okay. HO 8.1, first item, number 1. We've got N2 plus O2 for our reactants. Here's our arrow. There's our teeter-totter pivot point, creating N2O5. Ooh, for bonus points, how would you name N2O5? I'm hoping somebody said dinitrogen pentaoxide, maybe? A little review. It's always nice to review as we go. Okay, let's take a look at what we've got going on here for this particular homework item. Okay. Here we've got 2 nitrogen on the reactant side, and we've got 2 nitrogen on the product side. A-okay. We've got 2 oxygen on the reactant side. We've got 5 oxygen on the product side. Again, we're thinking of this arrow as our pivot point. On our teeter-totter, we must have both sides being the same. Well, our nitrogen are okay, our oxygen are not. So we need to get the oxygen to be the same. We've got O2 on the reactant side, we have O5 on the product side. Smallest number that both 2 and 5 go into. Lowest common multiple would be 10. Well, if we want to have 10 oxygen on the reactant side, we better have a coefficient of 5. We now have 10 oxygen on the reactant side. How many are going to need on the product side? Well, we've got O5 currently. What times 5 will get us to 10? That's going to be a 2. But that 2 changes something else. Remember that the coefficient multiplies to everything inside of that compound, just like a coefficient applies to our variable. Now we have how many nitrogen? 2 times 2, 4. What coefficient then will we need to balance the nitrogen in the reactant side? Well, we have 2 currently. We better add a 2 for a coefficient there. Now notice I added some extra space down below here to be able to draw my teeter-totter, to be able to start to label. If I needed to, I could label, okay, I've got 4 nitrogen here, and I've got 4 nitrogen on this side. Okay? I have found in the past that students find it incredibly helpful if you've got a separate sheet of paper to be able to keep track of how many of each type of atom you have in your balanced chemical reaction. Now, another trick, another tip, if I may, is as you start to balance these chemical equations, always leave the single elements until the end. Now, you'll notice here on the reactant side of number 1, both of them were single elements, just nitrogen, just oxygen. But if you look at number 2, you'll see on the reactant side we've got C2H6 and then just O2. Ooh, O2, why is it not O? Diatomic, Hofbrinkel. Oxygen always partners up to become stable. When you go to balance number 2, guys, I would strongly suggest you leave this oxygen, that O2, by itself until the very, very end. Because if you put a coefficient in front of that O2, it doesn't change anything else. If you were to change the coefficient, say, for the carbon dioxide on the product side here, if you change the coefficient here, it applies not only to the oxygen, but also to the carbon. So as you start working through these balanced equations, always leave those single elements until the end. Okay? As you continue to work through these balanced equations, it is a back and forth. It is a teeter-totter. If you've ever been on teeter-totter, you've got to go back and forth until you find the right balance. It is a back and a forth. You're going to be bopping back and forth from reactant to product side. As you continue to work through these questions, do not worry about that blank out in front. We haven't talked about what the different reactions look like yet. We're not going to fill that in until a later date. For tomorrow, please fill in numbers 1 through 25. Got to do a little practice. Try balancing these different chemical equations. If you'll feel bold, challenge questions. If you finish before the end of the hour, 1 through 25, balancing those coefficients, go ahead and work on 26 through 32 for me. Those are kind of challenging. Give them a shot. We're going to talk more about those actually when I come back and see you. If you want to work with a partner, that is fine. Do make sure if you're working with a partner though, make sure you're staying on task. This is our first item of this new semester. Start fresh, start ready to go. Make sure at the end of the hour, if you did work in a partner, please make sure you get your desks back to their original location. Please note I will be in before school tomorrow, so come on in and see me if you have questions. Okay? Again, this video is on Blackboard if you'd like to see the examples again, or if I moved a little too quickly and you didn't get something quite down, feel free to check it out on Blackboard. Thanks. I hope today went okay. Hope the technology piece was okay. I will see you guys tomorrow.